So let's continue with chapter 6 in the Whinstone Bridge configuration. Right here we are going to do an example application of where the Whinstone Bridge is used. Like I said, it is widely used for sensor manufacturing. So right here is being used for a temperature measuring bridge. So they are saying, they are giving us a thermistor is exposed to 50 Celsius, and its is exposed to 50 Celsius. But its standard reading at 25 Celsius is 1000 ohms. So they are saying that assume that when it is exposed to this higher temperature, the resistance drops from 1000 to 900. So now they ask, find what is the V out. So, excuse me. So to do that, oops, where did I go? No. Sorry. Okay, it's right there. So to do that, we have to find the voltage at this point and the voltage at that point. So here it looks cute. I can just redraw it so it's easier to analyze it. So if I want to find here, I understand that the potential value at this point is just the potential across B3. And the potential value at this point is just the potential value across B4 or R4. Why is that? Because from here to here, I'm going to 0. So to whatever I have here, I have to drop it here so that when I get here, I have to be 0. That's how I know that it has to be B3 and B4. So the B out is just going to be the difference between 3 and 4. Knowing that, I can use my knowledge of circuit analysis from chapter 3, chapter 4, where I analyze series circuits. So what I have here is a series circuit, so series circuits and parallel circuits. So I know that from here to here, I have 12 volts because this is go across of the voltage source. And then I'm going to split these 12 volts across these two resistors. So I can find B3 using voltage divider. So the voltage divider says that if I'm interested in B3, I'm going to multiply the resistor that I'm interested in by the source divided by the sum of the branch. So R3 divided by my R3 and R thermistor, which is what they are giving me to be 900. So it's going to be R3 is 1000, the sum is 1900 times 12, I get 6.31. B4 is going to be 1000 divided by R2 plus R4, which is 1000 each, is going to be 2000 multiplied by 12, I get 6 volts. So now I have B3 to be 6.3157, I have B4 to be 6 volts, so the V out is 0.32 volts. So the voltage is very small, but because we are in a balanced state here, we are able to pick that out, and then we can have lookup tables that can say, okay, when we are reading this voltage, that voltage is mapped into this temperature. So that's how actual thermostats work in your house. It's not like they actually measure the temperature. They are associating that voltage reading to a temperature so that you can see a number that makes sense on your screen, on your digital screen at home. So that's how it works. Applications of the Whinstone Bridge are widely using a strain gauge to measure forces, because it's so sensitive, it is so sensitive, so any disturbances can be measured and then mapped into voltages or into currents. Okay, let's continue. Thevenin theorem. This is very important. This is a technique that we are going to learn how to simplify simplify big circuits. Why is this important? Let's read the definition and then we are going to see why is it important. Thevenin states that any two-terminal resistive currents can be replaced with a simple equivalent circuit when viewed from two output terminals. The equivalent circuit is, we have a voltage Thevenin and a resistance Thevenin. So they are just in a series. Voltage is always going to come with a resistance that is in series to it. So once you are designing something, it's going to be massive. And when you present it to your customer, to other components of the design, you don't want to show your 1,000 components once. You want to show how the rest of the design is going to perceive or see your design, and that can be described in its totality by the voltage that is going to be producing and the resistance that is going to be loading into the connecting design. So that's why it is important, because we want to be able to divide the design process, but yet be able to connect it in a way that when we put it together, it will work properly. Okay? Yes, we have buffers in between to cut the noise, to separate different phases of the designs, but it's also important that the rest of the system sees or knows what is the voltage you're going to be producing and what is the load that you are going to be creating. For what? Because we want to avoid loading effects. Okay? So this is the Thevenin. There is another one called Norton, and what Norton is, it replaces the voltage by a current source, and instead of having the resistance in series, we have the resistance in parallel to the source. Okay, so we have Thevenin, and then we have Norton is for current. Then we have our Norton. So it is important. I think we are going to do an example of Norton in another video, or in the examples and problems for our chapter 6 section. But don't worry too much about Norton, because solving, Thevenizing a circuit, it's easier than finding the Norton equivalent. So the way we go around that is we Thevenize it, and then once we have the Thevenin equivalent, we convert this using Ohm's law into the Norton equivalent. Okay, so it's important that you know that. So Thevenin theorem. V Thevenin is defined as the open circuit voltage between the two output terminals of a circuit. Yes, we select a point that we're going to say we are going to Thevenize the circuit from this point, like a reference point. The R Thevenin is defined as the total resistance operating between 2 point terminals when all sources have been replaced by its internal resistance. So yes, we have to be careful when we have different sources when we are Thevenizing. So when we are Thevenizing and we are solving for R Thevenin, if we have a voltage source, we replace it with a wire, just a simple short. If we have a current source, we replace it with an open. Okay, we just open, we just remove it, and there is no wire connecting from there. So that makes the calculation simpler. When we are finding the Thevenin, then we have to put the source back. So that's important. Okay, so right here they give us the first example. So let's stop right here because this is going to take time. Let's leave this for the next video.